Today is day 7 of Unit 6. We started today just right away with the lesson, no warm-up today. And we started in the packet, in the Unit 6 packet on page 13. So you want to have that, you want to have your packet turned to page 13, but also you probably need your notebook out for some notes as well. So we first started talking about the difference between continuous and discontinuous graphs. Rational functions, the graphs are either continuous or discontinuous. And if you remember the graphs we looked at yesterday, the hyperbolas are considered discontinuous. And the reason why that they're discontinuous is because of that break in the center, that vertical asymptote, which if you recall was caused by the domain restriction. So that vertical asymptote causes hyperbographs to be discontinuous. So discontinuous means that there are what we call holes, which I'll talk about that in a moment some more, but there are holes or vertical asymptotes or both. Okay, and if there are either holes or vertical asymptotes, or a few holes or a few vertical asymptotes, or one of each, the graph is considered discontinuous. And the reason why is because if you think back to that hyperbola moment, we drew the first curve, we had to lift up our pencil to draw the second curve. So discontinuous, you must lift your pencil to draw the graph, versus continuous, there are no holes or vertical asymptotes. So if there's not a break in the graph, there's no holes or vertical asymptotes, then you may draw the graph without lifting your pencil. Okay, so that makes it continuous. So no hyperbolas are continuous, they're all discontinuous. And again, that's because of the vertical asymptote. Okay, so the next thing we did, a little bit lower on the page, we have these examples for example 1, and we're supposed to figure out whether the graph is continuous or discontinuous, and if discontinuous, where. So I'm looking at that equation, and I can see that that should look familiar from yesterday. We have a number in the numerator and an x in the denominator. We know that that graph is a hyperbola. So because it's a hyperbola, then I know that the graph is discontinuous, because I know it has a vertical asymptote. So the vertical asymptote we know comes from setting the denominator equal to 0 and solving. So if I set x minus 6 equal to 0, I get x equals 6. So there's a vertical asymptote at x equals 6, which is why the graph is considered discontinuous. So what you want to do for each one of these is you want to factor if you can and simplify if you can first. And then you're going to set the denominator equal to 0 and you're going to solve. So this b, I can, and by the way, we didn't do that in a because it didn't factor, it didn't simplify. So we just went right to setting the denominator equal to 0. So b, I can factor that. It doesn't simplify, nothing to factor out, but I can set the denominator equal to 0. And I can solve, and that tells me that x plus 1 equals 0, which means x is equal to negative 1. So because I just got a real number there for x, that means that this one is also discontinuous, because there's a vertical asymptote at x equals negative 1. Okay. So next one, we look at that, looks like it does not factor, so I can't simplify anything. So I'm going to set the denominator equal to 0, and I'm going to solve looks like square roots technique would be best there, square root of each side. So I'm getting the absolute value of x is equal to I, which means x is plus or minus I. So hopefully you realize, because we got imaginary numbers there, that means there's not a vertical asymptote, which means this graph is continuous. Okay, so what happens is, continuous, what happens is if you get, if you set the denominator equal to 0 and solve and you get imaginary numbers or complex numbers, then you will say continuous. That means I can draw that entire graph without picking up my pencil. There's no breaks. Next one, so we factor. We see a common factor, so we're going to simplify. I'm going to write the simplified equation, which, by the way, if you think about that, that's linear. Y equals x plus 2. That's going to be a diagonal line. So that's my simplified equation. So I know that diagonal lines don't have asymptotes, because remember what we said an asymptote is. It's a line that a curve approaches and usually does not cross. Sometimes it will, but usually it doesn't cross. But a curve has to approach it. Well, this is a line. Lines don't have asymptotes, okay, because the lines aren't curves. So this doesn't have any vertical asymptotes, but it also, but also I know that it doesn't have any vertical asymptotes because there's no denominator here. So remember how we figure out the vertical asymptotes is we set the denominator equal to 0 and solve. Well, it no longer has a denominator. The denominator is just a 1. So that's another reason why I know that this doesn't have any vertical asymptotes, aside from the fact that it's a line and lines don't. But just because it doesn't have vertical asymptotes does not mean that it's continuous. Remember, we would have to get set the denominator equal to 0 and get imaginary numbers or complex numbers to say continuous. So that means, based on the definition for discontinuous, I said discontinuous if it has a vertical asymptote or if it has a hole. This actually has a hole, and this is discontinuous. And I'll explain why, but let's write that. It's discontinuous because there's a hole. And we're going to figure out where the hole is in just a moment. Now, first of all, I know that there is a hole because I was able to factor and cross off common factors. Anytime there are common factors, then there are holes. A hole, or in this case, there's only one, or if there were multiple common factors, there would be multiple holes. Okay, so we do have one hole here because there's one common factor. So we need to figure out where the hole is. And a hole, by the way, is what it sounds like. It's an open point. Okay, so it's a point without anything filled in. So a point means I need both the x and the y. For the vertical asymptotes, we just listed the x because that was the equation for the line. Here I'm going to write this as a coordinate point. So to figure out where the hole is, I take the common factor that we factored out and I set that equal to 0. So x minus 2 was our common factor. I set that equal to 0 and I get x equals 2. So that's the x part of the hole. Then to get the y part, I take the 2 and I substitute it into the simplified equation, not the original, but the simplified equation. And so I put in 2 and I'm getting 4. So I know that there's a hole at 2, 4. Okay. So if I were to graph this, I would graph my diagonal line like I normally would. Y equals x plus 2, I'd graph normally. But then I would go to the point 2, 4, and I would put an open point there. Okay, and so what this demonstrates here is that these are all different rational functions, right? Like we can see all these look like fractions, y equals some fraction. But they take on various forms. They're not all going to be hyperbolas. And so what we just realized is sometimes rational functions will actually simplify to be linear. Okay, so this will be a line with a hole in it, of course. Other times they'll be continuous, and we'll talk about that more. Other times they'll be hyperbolas, and other times there'll be something that there'll be other graphs that we haven't even discussed yet. Like I said, we'll talk more about those in the next couple of classes. But just realize that rational functions, their graphs take on all different shapes. So the next thing that we did was we actually skipped 2 and 3 for now. We did example 4. And I believe I did change the problem here that it should say x squared plus 5x plus 6 over x plus 3. So we're going to go ahead and we're going to graph that without a calculator. So the first thing we're going to do, just like we did in the last example, is we're going to factor, if we can, which I think this one does, x plus 3, x plus 2. And then we're going to cross off common factors. Okay, so because I just crossed off a common factor, I have a simplified equation. And because I crossed off a common factor, I know that there is a hole. Okay, so I'm going to figure out where the hole is next. And I know that that's my simplified equation. So there's a hole. And remember what we did in the last one. We set the common factor equal to 0, so x plus 3. And we solve. And we have the x part of the hole. We put that x into the simplified equation. And we get the y part of the hole. So there's a hole at -3, -1. So let me list that. So I'm going to go ahead and plot that point on my graph here. So -3, 1, 2, 3, and down 1. And so I'm just making an open point. When you draw it, just make sure it's obviously open, nothing filled into it. Okay, so next thing I'm going to do is I'm going to think about the asymptotes. Well, this equation we said is linear. So a diagonal line does not have asymptotes, and we talked about that already. So, and the other reason, again, is this doesn't have a denominator. So if there's no denominator, I can't set the denominator equal to 0 and solve. So my denominator is just 1. 1 doesn't equal 0. So because of that, there are no vertical or horizontal asymptotes. None. I'm going to go ahead and get the x and y intercepts. So y-intercept, I'm substituting 0 in for x, and this goes into the simplified equation, not the original. So y is equal to 0 plus 2. So 0, 2 is my y-intercept. So I'll plot it. And x-intercept, excuse me. So putting 0 in for y, solving for x. So -2, 0. So let me plot that. Okay, now we have our points, so we're going to go ahead and graph by connecting them. When you draw the line here, just be sure not to go through the point. Make it obviously a hole. And then I'm just going to label the important points. Important points would be the holes and the intercepts. So -3, -1, -2, 0, and 0, 2. Okay, and that's our graph. That's our rational function. Okay, next. So we then went back and we looked at example number 2. And the only reason I did that was I definitely wanted to get to that last example, and time-wise we were kind of cut short today. So next we took a look at this. So once again, you start by factoring if you can, simplifying if you can. So looking at this equation, it does not factor, it does not simplify. So that means that because I can't cross off any common factors, that means there's no holes. Next, I'm going to figure out the vertical asymptote. So the vertical asymptote, remember, comes from setting the denominator equal to 0 and solving. This is VA. So x minus 2 equals 0, which means x equals 2. So x equals 2 is the vertical asymptote. So I'm going to go ahead and plot that. And label it. Okay. So next we're going to figure out the horizontal asymptote. And this is where you might need your notebook. I did give some notes in class today for how to find it, because there's several different scenarios we need to talk about. So the first thing that you'll do to find a horizontal asymptote is, step 1, you're going to find the degrees of the numerator and the denominator. So if I'm looking at this example here, I look at the degrees, and if you recall, we learned that in the previous unit, the degree is the highest exponent for each of the equations. So x to the first and x to the first, the degrees are each 1, 1 in the numerator and 1 in the denominator. Okay, so after you have found the degrees, then you're going to compare them. And so if you think about it, when we're comparing two numbers, we have three options. Either they're going to be the same, or the one on the top or in the numerator is going to be larger, or the one on the bottom or the denominator is going to be larger. So we need to look at all three scenarios. Since this example has the degrees being the same, degree 1 and degree 1, we'll first look at that, that scenario. So scenario 1, degrees are equal. Okay. So when the degrees are equal, the horizontal asymptote is y equals the leading coefficient divided by the leading coefficient. So in our example here, we already checked the degrees. Again, they were both 1, so they're equal. So I look at the leading coefficient, which is 3, and I divide that by the leading coefficient, which is 1. So I'm getting y equals 3 divided by 1, which is y equals 3. So my HA, I'm doing y equals 3 over 1. I'm getting 3. So y equals 3 is my horizontal asymptote. So I'm going to go ahead and plot that and label that. Okay. So that's what it is in this example, but we need to talk about the other scenarios. So we talked about what happens when the degrees are equal. Now, actually, before we look at the other scenarios, there is an exception to that. So I want to make sure I explain that. So I'm going to give an exception. I'll give an example. So let's say we have y equals, let's just say we have the same equation, but on the end, let's say I have a 10 added on. Okay, so I'm still going to, because this is rational, even though there's that extra 10 on the end, I'm still going to check the degrees, see that 1 and 1 are equal. And this rule tells me, okay, well then the horizontal asymptote is going to be y equals the leading coefficient 3 divided by the leading coefficient 1. So it's going to be y equals 3. However, we remember that adding 10 on the end, we talked about this yesterday, and really we've talked about this all year, adding a number on the end takes the entire graph and shifts it up. So if it shifts up 10, what normally would be y equals 3 has been shifted up 10, which means that y equals 13 would be the horizontal asymptote. So I still apply the rule, I still check, degrees are the same, y equals 3 over 1. But then I have to add that 10 on because the whole graph shifted up 10. So that gives me y equals 13 is the horizontal asymptote. Okay. So now let's talk about scenario 2. So we talked about when the degrees are equal. Now let's talk about when the degree of the numerator is larger than the degree of the denominator. Okay. For example, number 4 that we did a moment ago, we had, and I don't remember exactly what the equation was, but we had y equals x squared, I think it was plus 5x plus 6 over x plus 3, I think it was. Doesn't really matter if it's the exact same or not, but the point is the degree of the numerator is 2, the degree of the denominator is 1, and 2 is bigger than 1. So the numerator is larger than the denominator degree. So if you look back to that one we did a moment ago, remember that simplified to be a line. And lines don't have asymptotes. Okay, so when the degree of the numerator is larger than the denominator, then no horizontal asymptote, ever. Okay, so if the degree of the numerator is larger than the degree of the denominator, there will not be a horizontal asymptote. And even if I were to add or subtract a number after the rational part, after the fraction, there still would be no horizontal asymptote. All right, next. So last scenario. I guess I'll just kind of label these. So 2, you're checking the degrees, and either scenario A, the degrees are equal, B, the degree of the numerator is larger than the degree of denominator, or C, the degree of the numerator is smaller than the degree of the denominator. Okay, and you actually know what to do with that also, because I'll give an example. Y equals 1 over x. So we talked about that yesterday. We know that's a hyperbola, right? The degree of the numerator is 0 and the degree of the denominator is 1. So 0 is smaller than 1. So if you recall, when we graphed this yesterday, this most basic hyperbola has a horizontal asymptote at y equals 0. Now, once again, just like scenario A, there is an exception. So I'll give an example. If we have something like y equals 1 over x minus 7, then I still check the degrees. Degree 0 over degree 1, smaller numerator degree than denominator. So I would normally say y equals 0. But I'm recognizing the fact that that minus 7 means the entire graph, including the horizontal asymptote, which was at y equals 0, has been shifted down 7. So if it's been shifted from y equals 0 down 7, it is now at y equals negative 7. Okay, so with that's the horizontal asymptote, is y equals negative 7. So with this one, where the degree of the numerator is smaller than the denominator degree, and the first scenario A, where the degrees are equal, if there's a number added on the end, remember that number needs to be added on to the horizontal asymptote following the rule, but then add that number on. Or if it's a minus, you need to subtract that number. But if the degree of the numerator is bigger than the degree of denominator, like scenario B, then there's no horizontal asymptote, regardless of whether there's a number added on the end or not. That'll just always be no horizontal asymptote. Okay, so those are the notes that you need in your notebook. Now let's go back and finish our problem. So we did just figure out that there's a horizontal asymptote at y equals 3 and a vertical at x equals 2. So when you have this setup, you have one vertical asymptote and one horizontal asymptote, this graph will be a hyperbola. Okay, and we didn't know that right off the bat. The ones yesterday we looked at where we had a number in the numerator and an x or an x plus or minus something in the denominator, we knew right away they were going to be hyperbolas. This one we didn't know that, but now we do because we're getting the one vertical and one horizontal asymptote. So I need to figure out some points here so that I can plot my hyperbola, and that'll be done. So I'm going to get the x and y intercept since I need those anyway. Let's see. Let's try and separate our notes a little bit here. I didn't really give myself much space. X intercept. So I'm going to set y equal to 0. So remember, I can, anytime I want to, put a number over 1, and now I have a proportion that I can solve. So 0 times x minus 2 is 0. 3x plus 5 times 1 is 3x plus 5. So negative 5 equals 3x. So x equals negative 5/3. So my x-intercept is negative 5/3, 0. So negative 5/3 we know is negative 1 2/3. So I'm going to go ahead and plot that. Negative 1 2/3, so almost 3. Or almost negative 2, sorry. Negative 1 2/3, right about there. Okay. Next, I'm going to get the y-intercept. So I'll do that down here. So y-intercept, putting 0 in for x. So 3 times 0 plus 5 over 0 minus 2 gives me negative 5/2. So 0, negative 5/2 is my y-intercept. So 0, negative 2.5. Right here. So remember from yesterday that with a hyperbola, there's going to be the two curves, and what I said is you need to have 2 points per curve. So we have 2 points and we have the asymptotes as a guide. I'm going to go ahead and draw in the curve here on the bottom left section. So through that point, approaching the asymptote, approaching this asymptote, and through that point, arrows on the ends, that's the left part of the hyperbola. I am going to label the important points. So we have 0, negative 5/2, and we have negative 5/3, 0. And now we need the other half. We need the top part of that hyperbola. So I need to get some coordinates, some coordinate points to finish my graph. So I know that I need points from this top right section, and I know that that's going to be bigger than x values of 2. So I'm just going to pick 3 and, I don't know, 3 and 4, I guess, because those are larger than 2. So substituting 3 in, and remember I'm substituting here into the original equation. If I had a simplified equation, that's where I would substitute it, but I didn't simplify this. So 3 minus 2, that gives us a nice denominator, that's 1. So 3 times 3 is 9 plus 5 is 14. 14 over 1 is 14. I'm going to do my best, since this goes off my graph a little bit, but I'm just going to do my best to put this at about what 314 looks like. So 3 and then 14, I'm just going to put it up real high. And then 4, I'm going to, again, substitute in. So 4 minus 2 is 2, and 3 times 4 is 12 plus 5. 12 plus 5 is 17 over 2. Let's just double check that. So 4 minus 2 is 2. 4 times 2 is 12. 12 plus 5, 17. Yep. So 17/2 is, what, 8.5. So we're going to go to 4, 8.5. So 1, 2, 3, 4. That's 3. 8.5 is going to be a little bit lower than our 14 was. So now I have 2 points and I have these asymptotes to guide me. So I'm going to make my curve through those 2 points, getting really close to and flattening out that vertical asymptote, and through the other point and getting really close to flattening out towards that horizontal asymptote. So now I have my entire hyperbola graph. Okay, so that's how you're going to attempt your homework tonight, which is on a few similar problems. So you're going to have some that end up being linear with hole or holes, and you're going to have some that end up being hyperbolas like this one. So we did not do example 3 in class today. We'll do that tomorrow, and you won't have any like that in your homework. But you should try for homework worksheet number 2, problems 1 and 2, 5 and 7. So do your best to graph those without a calculator.